So the point of this lecture is just to get you to think about how we may go about developing an intuition as to how particle interact with that. And the reason we want to get this intuition is because if we want to interpret mechanistically observations we have with optical sensors, it'd be good if we understand what's the basis for that interaction. Otherwise, other correlations are better, but correlation can take you only this far in terms of your understanding as to why you observe what it is you observe. Okay, so the forward problem, and that's from Bowdoin, is if you have a particle of given specified size, shape, and optical properties, that is illuminated by an arbitrary polarized monochromatic wave, so that's this thing here, determine what's going to be the electrical field everywhere around it. And this is what my detector is. If my detector here or in that direction on the side, what am I likely to get? And of course, it's also a property of the environment, because it's the contrast with this environment that make this particle stand out optically, as we saw with these balls the other day. And I'll come back to this. These carbohydrate balls that when they swell, suddenly they become transparent. So we have, as you know, the soup of particle in the ocean is extremely varied. We'd love all of them to be exactly the same, all of them spheres, all of them simple, but they're not. They have cell walls, we talked about it, they might have calcium carbonates. So they vary in shape, they vary in size and pigment composition, and therefore they're likely to vary in scattering and absorption properties. And some of them even have very small variations on, this is the 5 micron. That spans about 5 microns, so this is probably like 1 micron. And see how complicated the type of shapes and how hard it may be to monitor. I think that we'll get to it at the end. We also have a whole bunch of non-algal particles. So those might have pigments that they got from the phytoplankton or not. And we have sand, silt, clays, or everything that's inorganic, and aggregate some mix of both, or mostly water, but with stuff in it. So we expect again that they will influence the optical properties, and the optical properties will be very different depending on which one is here. So what cell properties are likely to affect light? What do you think? What should I do? So we talked about some things that before. What are the things you think about? What is the pigment effect? Light, so it's absorbing. We saw with the least the size is affecting. What else? Okay. In what sense?
Both in how much certain molecules there are and different species incorporated.
Why would you defend light? What is it doing this? So composition in the sense that it affects the speed of light. So when we say refractive index, can be kind of confusing. Speed changes in the speed of light. So that's the real part. So this is speed of light as formulated as the index of refraction, and there's the absorption properties that's the and we get there. That's the imaginary, but that's the decay of light within the particle. So absorption is really so this causes scattering, and for absorption, it's that decay of light. Denoted as n prime. And just again, this is just mathematical convention. From your perspective, it's a fact light going through a particle is attenuated. There's a pigment there, or some molecule that resonates with that. Now with shape, it's interesting, just as I showed you, shape, there's gross shape, there's just general, the spherically, the little data, like a chain. And then there might be small variability on the, so, there's small features versus large features. Got the small patches as a whole bunch of bunch of okay. And ask questions if any of this makes no sense or it's not clear what I'm talking about. So size, and particularly as I love this from Matthew. Matthew came Sunday and we're looking at the Microsoft, and we see this giant atom chain, and he asked, what size does it have? What's its size? Is it, this part that might go through the filter? It's much smaller than its length, on which it gets stuck on the filter. What does the optical instrument see? Does it see this? Does it see this? Probably, again, depending on the environment, if the homogeneous turbulence, you have certain probability to see every possible direction. So size, it's a tough, it's a really tough thing, because we're taking something extrusion effective as a data chain, and we're trying to give, and we want to give a single, something that does like this. We have plenty of them here, and we're trying to practice them with one geometry. And the reason it's semi-successful is because, again, if you look at this microscope and you play with the magnification, we have things that are 10 times bigger than this, and we have things that are 10 times smaller. And this aspect ratio might be 10 to 1, but it's still compact relative to the large infinite or other large things running around there. And it is significantly bigger than the tiny ciliates and the lamella and other things we can place. So it's simply because we have such a large range of variability in the ocean in terms of size that we can kind of avoid shape, but kind of. And when we then think of models for them, we have to think about what it is that I'm trying to compare. How do I compare it to? So if I'm interested in comparing mass, I might say, okay, what's my volume? And then I'm going to say, okay, I'm going to take a sphere with equivalent volume, and I'm going to use that its diameter as the equivalent size. But it turns out that optics, particularly when you're larger than the wavelength, you're actually most sensitive to cross-sectional area. So with optics, it's actually a sphere that has the same cross-sectional area that might be a little bit of a better model to understand how optics work. Geometric optics, when you see it, really large compared to the wavelength. The only thing you see is the shadow. And there's a wonderful theorem from 19th century French mathematician called Cauchy, and that's for convex shape, things like fiber magnet. The average cross-sectional area over all radiation, average cross-section equals to a quarter of the surface area. 1/4 of the surface area, and you know that it's true for a sphere. equal, this is the average cross section over all ranges. So if the ocean is turbulent or we're measuring, we're getting something here. So composition, we said it's the bulk index of refraction. How different is the speed of light in my particle and the water around it? Shapes, we talked about macro and that's the smooth and micro, the little departure for smoothness. Internal structure, when we look at this microscope and it still sat there, and we collected the net yesterday to show Chelsea, and we spent I don't know how long just saying ooh and ah. What you see is that these long platinum chips have organelles, and these organelles are, little things like this, the gold class is sitting in things like this. But when you look at a serration, suddenly, it's completely filled with this is green. Every one of them has things distributed within them very differently. And you can imagine if light that goes here is going to be different than light that interacts with this internal structure. And there's cell walls, and the different materials on the inside. There's vacuoles, there's places in those diatoms where it's mostly filled with either cytoplasm or some lipids. And then we also have this very, very diffuse particle that nectar you. And then the question is, how solid is this particle? Is it, how packed is it? Can I see through it? Can I not? Do I need to model it with a bunch of individual particles? It's completely not clear. So why do we care about it, and why the me solution? So me solution is because we care. That's we have a solution, so we got to use it. We have a model. Why not use the model we have? But also they provide a whole bunch of utility for us. We calibrate flow cytometers, we calibrate backscattering sensors, and the lease itself, if you want to check that it really gives you the volume scattering function, you can buy precision beads for which you expect really. And so by understanding how light interacts with those beads, you basically use that to calibrate your instrument. And what, so in essence, what signal am I expecting to get from something? We have 3 students that took this class that used me theory for their thesis. Rebecca Green used me theory in flow cytometry. So flow cytometry, you basically infer size from forward scattering. And to understand how that happens with a phytoplankton, not your bead that you calibrate against, and what's the difference, you need to do these calculations. She has a whole paper about how to use, how you calibrate flow cytometers more accurately than was done in kids. Giorgio used, actually this was after his thesis, but me theory to analyze the heat cycle in optical properties observed in crucible. And Tio has a whole size algorithm from space based on it. So people have found it useful. There's a paper I love, which is from us, AAS, a Norwegian scientist, mostly wrote paper by himself. That's some people do that, and the paper cornerstone for whole field, where he's trying to build the refractive index of phytoplankton just from its components. So he goes and he takes individual species and then looked at how much protein there is in them from the literature, how much calcite, how much carbohydrate, how much fat, how much alcohol. These you can see have each a very different index of refraction. Then he goes and add different water fraction into it. So he's basically doing this experiment. And finally using, there are equations that allow you to take mixtures of things of different index of refraction and calculate an effective index of refraction. And doing that, he fell right on the type of index of refraction people had reported based on optical in the Bicot and Morel papers in particular. And what he found also that on average, so this is index of refraction relative to air. This is why water is 1.34, yeah, but 1.34, and this is 1.38, so it's slightly above water. With the ratio, it's 1.4, 1.6 here for all these different groups of algae. This is for 80% water, which was found to be the average reported in the literature, based on dry weight to salt to the total weight based on a whole variety of different ways. So I just went and did a shopping spree at the time there was no internet. We had to actually read papers and go into the library. But it's a beautiful paper on how do we get to this index of refraction on the order of 1.05 for fiber. You'll see us use a lot. So 1.05 is kind of and around that is the classic value. And it goes to 1.1. So this is what he's finding is that it's for 80% conning, that's the biggest driver, water. The water conning of fiber are the biggest driver to their index of refraction, which otherwise has in it all these other things that have a large variability in index of refraction. The inverse problem to how to get to the index of refraction is what Brico and Morel did in a series of papers where they taking measurements of optical properties of phytoplankton that they measure in the lab culture, they measure their size, they then feed it into codes and they find the optical properties of the particle that will match the best their optical observations. And from that, and then infer what's the imaginary and real part of the index of refraction going into this culture. These are cornerstone studies in our field. And we'll do similar calculations inside. So you make measurements on a known culture, but you don't know its optical properties, and you're finding by an inverse problem what are my index of refraction, size what's the index of refraction that will give me my observation. And these look a lot like, these are efficiency factors, but if you remember, so you have to multiply them by cross-sectional area, et cetera, to get to the actual phytoplankton properties. But if you remember, these look a lot like your cultures. This is QC, this is the attenuation, this is QB, and this is QA. But this is really proportional to absorption, scattering, and attenuation. When you did the Donaliella and when you did the diagram, they looked very similar to these, the measurements, remember? So this is an exercise you could do with the culture. You can exactly go through the same. But they did it first. And the other thing you have here is anomalous dispersion. That's the fact that when you're close to an absorption peak, it's affecting the real part of the index of refraction. You have to take it into account.
We just mentioned they did it with the benchtop study for tunnel without an integrated sphere. They changed the optical configuration of just the standard spec to DC or absorption. They turned it into an ace gas just by changing the pollination of the beam and incredibly.
So here we go through this process of absorption relative to chlorophyll. And this is from a super study by this is a slide from Colin, but it's a super study that Heidi Sosik did way back. So you start with a molecule, and if you only looked at that molecule after you burst a cell, and you look at the absorption by this molecule, this is kind of absorption you're going to measure. But now you stick it in a chloroplast. Getting a chloroplast, and suddenly there's changes in the absorption. And now you stick it in a cell, and it's even more different. You see the reduction in absorption in these cases. So there's, and in the environment, it's in the cell. It's not recorded. So this has a variety of implications, but among them is how we, and this is we talked about in the field a lot. Are we more interested really in this? If what we want are properties related to absorption, maybe we should not try and get chlorophyll and then get absorption from chlorophyll, but rather use absorption, try and do inversion to absorption directly. For example, for primary productivity. Should we grow this productivity into models that are chlorophyll based, or should we go to models that are absorption based? Because that's the process that captures photons. It's based on absorption, and then using the absorption could remove some biases that are there if I'm trying to get chlorophyll and do everything from the chlorophyll molecule. You'll find that in the literature. So this change as you put things in chloroplasm in the cell is called packaging. And it's a function of both of size and chlorophyll concentration. And the kind of basic paper on the subject is by Dorsens from 1956. So it's been known for a while, but it's not new. It's something people have known. And it also occurs that there's a certain relationship with chlorophyll over broad ocean that are very useful. It so happened that when you have a lot of chlorophyll, cells tend to be larger, and they also tend to be more packaged, meaning the ratio, if you will, of blue to red absorption is going to be smaller. But generally speaking, you're not going to get, see, this is the ratio, this is the blue to red. So an unpackaged cell is going to, it's from a package ratio. This is from a paper by Glicon, and it's still used a lot in the literature as the way to model chlorophyll-specific absorption by phytoplankton. So you have to multiply by one more chlorophyll to get the AF cell. And this is absorption by phytoplankton divided by chlorophyll. And she has a table for A, and she has a table for B. And this is kind of an average for the ocean. Whether it's going to work exactly where you are, not necessarily, because it would be influenced by light, by species composition. But as a general rule, would it work if you're trying to do a global algorithm for the ocean? It would work much better than if you not count. So, yes, sorry.
Just a question about the bigger amount, right?
Yes.
So that's normalized.
Normalized to 1 here at a specific.
So what's that figure?
So it's exactly the same as these, just the variability in the curve. Okay. So they're all normalized to 1 here. So there's a change in magnitude,
Yeah, I get
as well as in shape.
Okay.
That's the point. You're welcome. Thank you for asking. If you're asking, or any one of you is asking, probably there's 10 of you that wondered and just felt uncomfortable asking.
I just want to challenge you to think about what doesn't obey that rule that you just said, that when you go to high chlorophyll waters, cells tend to be big. When you go to low chlorophyll waters, cells tend to be small. They're under the ocean. For example, where you might have really high concentrations. Give an example. Where?
Here, the sound here.
Maybe. I was thinking that you can have a harmful algal bloom with a very small Ariocarpus. So brown tides in Texas and on Long Island, you get really high concentrations of biomass. But all the cells, it's a monoculture, 2 micron cells. Right? And so they're going to have very strong peaks, small cells, with very large biomass in the water. So they have in an area where you have big cells, which is not a lot of big cells. So, but Emmanuel was saying is that this is pretty critical to the dynamic of the ocean, particular environment. This will make the logical relation between plastics.
So, and this brings another thing over. This group, we call Morelli, and a lot of people working with them, discovered broad brush relationship between chlorophyll and everything else in the ocean. And they were robust relationships. Because chlorophyll can provide us an order one description of a lot of what we're seeing in the open ocean. Again, in average, in everyone's specific place, specific time it could be open, but generally speaking, there's a relation. But then you look at these NASA's product that are distributed to us, and there's promotion color, and there's 20 different products. There's a different product of POC from chlorophyll for a whole variety of things, for size. And when you look at correlation between them, they correlate tremendously well. Tremendously. And then the question is it new information? Am I getting, when I'm using a size algorithm, is it independent of chlorophyll, or is it basically the same information I have in chlorophyll, just with a different name? And the issue is important is because modelers don't know this, don't know that these are basically correlated because of the effect on the color of the ocean, and assume these are different ecological information that help them constrain the model maybe better than it really is constrained. So it has implication whether these products are independent and sometimes agree, sometimes disagree, versus they basically do the same. It's something just to think about. So this is a different perspective to look at packaging. So if you run a meat code, as we do today, what you'll find, and I show you some results of these in the attenuation talk. What you'll find is if you look at an absorbing substance, and now what I do, as I did for beam attenuation, but I didn't describe it like that, is let's say I have a substance, and I have a certain amount of substance. Something that has an index of refraction, it changes the light speed, it also changes it has absorbing properties. And I can choose to have it, in tiny particle, in the same amount. I can choose to have it in, a few bigger particles. Within a meter cube, I can choose to have it in one big one. And this is the exercise I'm showing you there. There, basically what I'm showing you is the absorption per volume of one particle per meter cube. Okay, that's what I'm doing with this calculation. But it can be so this is one particle. If it's this guy, it's because it's per volume, the numbers are going away. So it's basically I'm doing it for every possible size of those particles. And what you see for absorption, for attenuation, we had in the attenuation calculation this resonant. There was a place where I had the most benefit. Remember, there was this resonant thing where you get the most attenuation per volume as function of size. For absorption, it's different, and it's really, really cool. Some of it I just thought about recently. So you start as a dissolved substance, basically. You're much smaller than the wavelength. It's kind of constant. There's some small changes because of index, real part of the index of refraction. So this is like phytoplankton, and this is like quartz. But overall, there's very little. It's very little change. And then suddenly there's an area where actually I'm absorbing even more than when I was dissolving. And then finally, here, at around 10 micron for this case, so this is an absorption peak 676, strong absorption value, relatively strong absorption value. I'm going down like 1/4 diameter. So my absorption is not as efficient. That's the packaging issue I'm talking about. As you put more material in a cell, it's absorbing. When you're really large and the cell is very, very absorbing, by the time the light goes here, nothing is left. So this is not efficient. On the other hand, if it's slightly absorbing, I can have, and it's refracted, I can have the light bounce several times here, and then it's absorbed. And this is how I get this extra peak in between. It's just the light that's bouncing inside the cell just like in an integrating. And I can get even an increase on the order of, I don't know, 20% there in, where did I put that? In this, in absorption. This is an increase in absorption compared to the soil because of refraction inside the stuff. So this is how packaging comes about. Packaging comes about because there's a point where there's all the absorption happens before you even interact with the material. So this is a different way to look at this phenomena of packaging, and you can see why it occurs more in strongly absorbing. See here, there's very little absorption, so we don't see much packaging. It's not really. But here, where you have strong absorption, so that's where you're gonna see the effect of packaging. Okay, so enough with absorption. Now I'm going to talk about something else. So this is a property, backscattering ratio, that from for a very long time I thought would be mostly affected by size, because you know how you get more and more forward peaking your scattering as you get bigger. So you think a priori, this is it. This is the size that I have a new index for size. Wonderful. And then I did a bunch of recalculation, and it turned out for the kind of sizes that we have in the ocean, it's mostly affected by index of refraction and not by size. It is affected by size when you have very steep size distribution. But mostly, if you take a specific slope for the particle size distribution, remember we said 4 was the kind of canonical value for open. Coastal will tend to go in this direction. If I look and I'm looking at the backscattering ratio, what I see is it's mostly changing due to. And then if you go in the environment and you throw all of your observation on it, it kind of makes sense. This is from coast of New Jersey. This is what we're getting, an estimated periodic slope from the beam attenuation. This is the backscattering ratio, and underneath it is this schematic, is the same plot coming straight out of meteor. We take into account acceptance angle and stuff like this. So it's a small correction of the previous one. So 55,000. This is from near a beach. We're right next to a beach. And this is the open ocean data. And look, we factor almost 6 in backscattering, which we think is due, we did not do the measurements, is due to composition. Inorganic, organic, something. Now we'll talk about shape, but I'm going to get back to it because something that should have disturbed you, and nobody said anything, is how dare you do backscattering with meat? Now we talked to you before, we said meat should not work for backscattering. Yeah, the backscattering ratio is totally based on meat theory, we didn't account for any internal structure. Should have showed me that quote from Bowdoin that said, "Don't model if you don't have a good one." So this is now shape consideration. This is a plot from that's based on data collected in California by some water quality management thing that looks at the big microscopy for many years. And where we find that on average, cells tend to be elongated like a football ball, much more than plate-like. This is a much more prevalent shape with a, you can say, a modal axis ratio of about 5 than something that looks plate-like in their phytoplankton collection. There's very little in the literature, not in environment. So things tend to be more elongated than they tend to be plate-like flat. They are plate-like, but like synodiscus, but they're rare. They tend to have not very big departure from sphere. Sphere is one. That's the expectation. So here is a sphere, here is a plate-like oblate, and this is called a oblate. Football shape, plate shape, and a sphere. That's the next level of complexity to think of beyond the sphere. So in one axis, so now I have I have two, or shorter, I have two axes that stay the same, and only one of them I can play with. Try and describe it. So with Elmina Cravano, we did a review paper on what was available at the time. And for example, what you find is that if you take glass spheres of a given size, and then you sieve natural particle, you will get slightly different volume scattering function because of those elongations. So it affects the volume scattering function. There do exist codes out there. This is from a slide from Volton. By the way, Volton is a really pioneer of scattering measurement. She is Dutch, and she has published a whole bunch of volume scattering function for cultures, for dust, for a whole really pioneering work, including polarization measurements. But this is a slide that, from a presentation she gave, where she talks about the different theories one could use for different sizes, because they don't, there's a thing called T matrix. There's a whole variety of codes out there, but they do not necessarily span all the axis ratios you're interested in and all the sizes you want. So the size limit using T matrix, that's limiting in terms of what you can say. And this is just an example from a paper by Latimer, but it's in Bohr and Hoffman as to why you're getting differences compared to a sphere, as it's orienting in different direction in terms of how light is going. This is just with an axis ratio of 2 and a phytoplankton. So you can see that this resonance feature that you've not seen yet, but you've seen in some of your runs this afternoon, change depending on what is directed towards the light. And also reflected light is changing. And this is what, in general, it causes different electromagnetic interference between our particle and the light that impinges on it compared to a sphere. So it's not totally surprising. So here is a little exercise we did in the lab. It was headed by my wife, who's on a glacier in Greenland right now. She grew up a culture of Soratium, like the ones we had in the lab. And with the help of a Brazilian undergrad that ran our lab when Laura Azevedo, when we just started at UMaine, she grew these and ran them in the list. And when you run them in the list, you run this culture in the list, you get 3 peaks in the inversion. One peak, this one is associated with the thickness of these guys. So that contributes to the volume scattering function in the longer, higher angle. Then you have another peak, which has to do with this part. And then you have another peak that has to do with the whole. So this is one cell, and see how it changes your size distribution just due to one cell. You get 3 peaks. Another thing that they did is run another forming species from California. They ran it, and the observation from the field published by a group from USGS and in the lab were right on each other, spot on. So if you wanted a tool to see the harmful algorithm in the field when it's on its own in the monoculture, the least could do it for you because it stands out in a very specific size. And then another thing they used it for creatively is to see sexual reproduction in the lab, simply by running your culture through this, not a microscope. And so this big jump in cell diameter, when diatoms have sex, they gain size because as they divide themselves, the average size goes down. Anyway, cool application of the list and its ability to get size from the theory, et cetera, to do science. These are some results from Cavano's paper quantifying how shape affects your spectrum. This is gamma dB. So yeah, so it affects your this gamma is actually the ratio of a cell that has a certain aspect ratio, it's backscattering, compared to a sphere that has the same volume. How different would they be? Because we're trying to look at things that have different mass, but you see that in general, you can have in certain parts of the size spectrum significant differences. And of course, they get stabilized and bigger as you go all the way towards large particle, because now it's a cross section. When you're very large, it's all cross. And spheres are unique in that they have the least cross section of all these spheroids, and actually of all probabilities. They have the least surface area to volume. So sphere is not an average particle. It's an extreme particle. Surface area. So we understand why, and this is for B, for total scattering, this is for PV, no need to get into it, and this is for different indices of diffraction. But the point is just to think, okay, shape will affect my backscattering, and the backscattering will be higher if I'm non-spherical compared to spherical. So that's another way to look at this enigma of backscattering we've heard about. The second thing that can give you higher backscattering is even if you just look at cell wall and material image. So now I have a concentric sphere with a cell wall of different material. That alone will cause an increase in the backscattering. This is an old study by Miller in 1979. A very nice study where he basically divided, instead of it looks at the result with a me code of a homogeneous sphere, which is the cell body, a holosphere, which is the out, and then both of them together. And concluding that the biggest contribution of the holosphere, the membrane outside, is to increase the backscattering. These oscillations, you'll find that there are resonances when you use a single size indicator. The moment you use a size solution, even a little wider, you're not going to get these oscillations. But we'll do it this afternoon. You'll see those oscillations, and you'll see how we might. And this is the Organelli study. Already you heard from Wayne about it. I'm just putting in sake of completeness. If you try to, if you model particle in the ocean as coated sphere with a inside index fraction of 1.06 and a shell index fraction of 1.13, you can reconcile both backscattering and attenuation measurements measured along the A and T curves. Now, another evidence that backscattering is different than what me would give us is here we have results from a study by Stramsky in 2001, where he looked at properties of many different phytoplankton and marine particles. So Stramsky tried to basically build up all the backscattering and other optical properties that are likely to be found in the ocean, but by dividing it into all the possible phytoplankton and non-phytoplankton, et cetera, et cetera. And what Amanda Whitmire and other students from this class did in the thesis is just run a whole bunch of measurement on culture with the instrument available at the time. This is the hydrostat 6, this is the BPP. And what she found is when she looks at the cross section, this is a cross section. So so she divided it, it's beam attenuation divided by the concentration of particles. When she does it for scattering, her measurements agree quite well with those of Stramsky. So me theory seems to be consistent. But when she looked at backscattering, her backscattering was significantly higher than those. One thing to notice that these were not axinic cultures. There might have been significant, even though they were in exponential phase, there could be NAC in them, and that could also contribute to those differences. So this is a valid criticism we got after that. So now a paper by Gordon, when he looks at these coccolithophores, and he's trying to model, what is this? Is this important, this little variability to the optical property? And the way you do it is using this, you're building a model, and you're using these dipoles that you're gonna put in your model in specific ways. The discrete dipole approximation, which is a very good way to develop an understanding as to how things scatter, but it's extremely computationally expensive. And you have to do one for each, each stroke when you put them together, and it's very intensive. So that's why you get a whole paper for doing one cell or one feature of a cell. But what's important about it, the bottom line of this paper is that the goal of the study was to obtain some understanding of the differences in the backscattering of a collection of such objects in random orientation, and a collection of randomly oriented homogeneous disks of the same size. In this regime, so the regime of size that is this car, which this is 1.5 micron in diameter, the backscattering is totally governed by particle gross morphology and effective image reflection. So I do not need to bother. What he found out of it is that you do not need to bother with these because they're so small compared to the wavelength that they're not affected. Scattering happens when things are about the same size as the wavelength. So now I'll go into another subject that I enjoy looking at, aggregation. So now we're talking about these things in the ocean that are there, whether you want it or not. So this is from a tripod off Martha's Vineyard, 14 meters of depth. So this is aggregation tested to roll. So the bottom processes, so 12 meters of depth, which is 1 meter above buffer. And this is how, within just one day, the storm passes and your water is completely dominated. Before the storm, water is dominated by particles that are bigger than a millimeter. And when you look in the camera, and a day apart of the day, things are smaller than 100 microns. But we can have these things, particularly in coastal environments, but as well in open ocean as a mechanism to transfer carbon to depth. So we want to understand how to model things like that. And thank you for our atmospheric colleagues because they were thinking about it before us. So there's a paper from Latimer, 1985, where it tells you basically, if you take a hollow shell and add to it a spheroid divided by 2, you're going to get something that will give you both attenuation and scattering properties. And he compared it to a whole bunch of balls that put together. And so now you can think about again. So now same diagrams as before my previous lecture said. Beam attenuation, I have volume of the particle, solid fraction. But now I'm dealing with things that are mostly water. They're mostly water, but not in this sense. This is mostly water in a phytoplankton. This, but now it's something like this. There's a loss of loose particle and there's water in between. It's not the same as this. But again, there's some index of refraction, effective index of refraction. F is the water, is the solid fraction. So 1 means I have 99% water. F means I have 1% water. So I'm using his model, this model, with these solid fractions. So I'm diluting the index of refraction as I'm changing the particle. And then I'm using a ratio that's based on published literature to tell me how much, as my aggregate is growing in size, how much more water there is in size. They use something called fractal dimension for it, but you don't have to get into that. In essence, what it says is how much water do I have versus solid in my particle. These are these dots here. These dots. And what's really cool is that you see that beam attenuation to the volume of solid fraction, if I use those, I'm not changing much as function of size. I have here almost 2 orders of magnitude in size, and my CP to volume is almost non-changing. While if everything had the same fraction of water, I have huge changes as function of size in the environment. So if all the aggregate had only one kind of amount of water in them, I would be very variable in beam attenuation as a measure of SPM, as a measure of mass, as a measure of material in the water. Because my solid fraction is my TSF, my total suspended particle mass, or my POC. So this helped to explain why in my previous talk I told you that we don't see large changes in beam attenuation to mass in the environment, in the Hill study, compared to what we would expect if they were single grain, solid particle. If they were single grain, they would have much higher dry mass. And so as the particles get bigger, I'm going to get much less attenuation for mass. And I would be much worse in predicting attenuation mass from attenuation. So in essence, aggregation approximately conserved area. What we're conserving is area of particles. And because they're so loosely aggregated, I'm not losing the area. They're not shaping each other, making less size dependent. It's complicated, I know. But what's really cool is that Wayne and I worked together on this problem, and this is Wayne's thesis, where one of the big part of it was looking at how aggregates change optical properties. We were working with Paul Hill. Paul was making this camera measurement. We had AC9 on the bottom of the ocean, a whole bunch of other things. And one of the most creative things Wayne did is lab experiments. So he took an AC9, put it on the bottom of the sink, a list, put it on the bottom of the sink, heavy instrument, put it on the bottom of the sink, made a big slurry of Arizona lab dust, but it was different Kelvinite, I think it was, and then added to it a salt that would cause it to aggregate. So it's an inorganic aggregation. And as the aggregate formed, then you started to saddle fluorines. And then he also collected, he and another student, they would collect, because we had also acoustic instruments, they would collect the TSM. They would collect it with a syringe from the level where the instruments were measuring. And so they could look at mass normalized optical properties as the average size of the aggregate groups. So the list is telling us, this is a function of time of the experiment. So they would go for 3 hours, 3.5 hours. This is SPM here. So this is SPM, these dots, the total suspended mass. But measured on a scale, varying from about 10 to 30 per gram per meter cube. This is the size of the aggregate as inferred from the base. And we also, they took some samples from microscopy which were consistent. This is how the optical properties were changing. So you have beam attenuation based on the AC9, you have a beam attenuation based on the list, and you have backscattering from an ecosensor. And then if you normalize them per mass, this is what you get. A relatively constant value, you have to multiply by 10 to the minus 6 beta beta. Overall, very little change in property per mass as the aggregates were growing, which is excellent because it means that we can use optics as a proxy even in the face of aggregation to infer mass. And that helped to explain the paper from Paul Hill that came the same year as to why this ratio, this beam attenuation per mass, seems so constant in many, many studies from all over the planet at around a value of 0.5. Even though it's different composition, different everything. So, I mean, that makes the same point I made so far, so I don't have to repeat it. Another thing that Wayne did was to put two of these side by side on the dock in the I don't know if we talked about it a little bit on the dock in the Damariscotta River, And then one of them have a pump near the intake of the leaf to break the big particles, the aggregates that you would see in the leaf otherwise, if both are. This is 10 minutes where we put them measuring exactly the same side by side. So you can see the two agree. And then one with a pump that breaks the big aggregate, and suddenly you see them appear, the particle appears in a small fraction. And the beam attenuation of the two was not very different. The volume scattering function changed a lot, but overall, the beam attenuation of the two, when we did that, was not very different. So we got very different mean size from the inversion, but overall beam attenuation did not change, orders of magnitude as we're breaking solid, because it did not break solid particle, it was aggregate particle. So small effect on beam attenuation, but large on near forward. Which also tells you that if you work on a boat and use the inline system, and you change, there's no way, when you pump water to your boat, you will change the size of particle if they are aggregates, fragile, breaking particle. But your estimate of the beam attenuation might not change a lot compared to what it was in the environment. And you should always check it with samples as well. So to summarize, and this is, by the way, one of the funnest things I've ever done. It's me as a postdoc with Ron Zanabel in the background with an AC9 on my back and a CCD and a hose in my hand where water was coming into the system. This was done in the Bahamas in 97 and 98. There's still a lot of work to do in oceanography. We need to account for diversity of shape. We need to account for internal structure. So far, none of the model has the internal structure really well described, and account for the diversity impact. So all of these are for you guys to do better than we have. And both theoretical and observation advances are needed. And there's a lot of hope, and you haven't talked about polarization, that this could add more information that could help us constrain more about the particle than we can currently do. Now, what's my dream view for the field? So one thing that's nice for us in oceanography, the atmospheric scientists have done most of the work for us 20 years ago, because there's much more money going into atmospheric science as weather, but they come up with really, really interesting approaches that we can learn a lot from. And one of which is the one for Aeronet stations. So Aeronet stations are all over the world, and they're designed to provide information on the atmosphere, but by doing remote sensing with optical. So they're looking up into the sky. They have this radiometer. They would look around the sun. They look directly at the sun to get the beam attenuation, around the sun to get information about the VSF. They do a variety of measurements. And when they combine those with radiative transfer modeling of the atmosphere at the same time, satellite data, they're able to get information about gases absorption, molecular scattering, calculated for given pressure, and aerosol absorption scattering. So by bringing more information from different kinds of measurement, they can constrain much better using what kind of aerosol they're in there. And that's really my hope for us in our field. And they use libraries of single particle optical property. They use radiative transfer. They use a whole variety, all the tools they have in the game. But the bottom line is really the more information we have, the more properties we can constrain. Oleg Dubovik is one of the big drivers there. Amazing. And here is an example. Here is a single scattering albedo. So this is scattering over beam attenuation as function of wavelength. This is in micron for a given place at a given, for 4 different Aeronet station, and it's different. And they give you the size distribution of the aerosol that came out of the inversion. So you can imagine if we took, instead of measuring a few optical properties that we do on profiling floats, now we do fluorescence and backscattering, but we also do now radiometry on them. If we took all those together, we might be able to better constrain the underlying particles that are in the planet. So the more measurements we have that are different in terms of the information, the more we can constrain what's in the mind. And bringing approaches that include remote sensing to it, because that's more information about where our flow is coming up, could also help in terms of constraint. Spectral information, so you won't have the current flows and things of that nature. Very close is putting hyperspectral radiometers now. So that's, will open more information. The more you bring different measurements, the more you'll be able to better constrain the underlying distribution of